Now, in the last lecture, we had looked at the structure of the vortex. The vortex structure is shown here, where you have in this red is the normal core region, and it is surrounded by the superconducting region of the superconductor. So this is the vortex. What is shown in red here is the normal region, and the superconducting order parameter goes to 0 in the center of the vortex over a coherence length xi, which is the radius of the vortex core. The order parameter decays down to 0. The form of this order parameter, the decay of this order parameter is this tan hyperbolic x by square root of 2 times xi, which we have already derived earlier. For a normal vacuum interface, we had shown how the order parameter goes to 0. This is the same way the order parameter goes to 0 inside the vortex core. Now, around the vortex core, the magnetic field distribution is shown in green, where at large distances, the order parameter decays as exponential minus r by lambda divided by square root of r. Exponential of minus r by lambda. So at distances much larger than lambda, it is exponentially decayed out. It is very small and it goes down as e raised to minus r by lambda divided by square root of r. But once you are inside lambda, here the change is much more slower. The value is much larger, and here it is phi naught by 2 pi lambda square. The value of the magnetic field inside goes as log of r by lambda. So it is roughly a much more slower variation. It is roughly constant, and over the coherence length you consider it roughly constant, and over the coherence length over the vortex, the magnetic field is phi naught by 2 pi xi square. So this is how the magnetic field varies across the vortex, and around the vortex there are currents which are circulating, which are actually shielding the magnetic field from so when you apply a magnetic field, the magnetic flux inside the vortex core will be present because it's a normal region, but outside it, as it is superconducting, the magnetic field will be shielded out. And so there are screening currents which are shown in black, which are circulating around this vortex, which will try to shield the magnetic flux and decay it, and it is because of this reason that the magnetic field actually decays down outside in the superconducting region, and this gives rise to the shielding currents. And these shielding currents are we have also derived from Maxwell's equations, which we had shown here, that the current density J is phi naught by 2 pi lambda cube mu naught k1 r, where this is the first modified Bessel's function, and this goes if you take within lambda for a distance r greater than the coherence length and much less than lambda, namely within this core region where the flux is roughly constant. Within region, the variation of the current density is shown here, and the variation in the current density within this region is given by phi naught by 2 pi lambda cube r. We had already, and theta cap is the direction in the for the cylindrical polar coordinates. Okay, so this is how the current density inside the lambda, inside a distance lambda of the center of the vortex. So within this region lambda, this is how the current density varies inside the superconductor. Okay, so now we would like to actually calculate the what is the energy of a vortex line. Given that there are currents and magnetic fields associated with the vortex, we would like to calculate what is the energy of a vortex. Now basically, if to calculate what is the energy of a vortex line, what we consider is the following. We will do some approximations for this, some approximations which we will use. It can be done exactly also, but the approximations we use are quite accurate. So basically this is the vortex line. Okay, this is your vortex, and this is the coherence length. The radius of the vortex is coherence length, and within lambda distance of all our calculations, will be, all our calculations will be within lambda, as outside lambda the fields and currents decay out exponentially. Okay, so all the magnetic fields outside lambda decay out exponentially. So all our calculations will be restricted to distances which are within lambda of the vortex. Okay, so within a distance lambda of this vortex, we will consider all the effects of the currents and the magnetic fields within this region. Okay, and within lambda, the average local field B is roughly phi naught by pi lambda square. This is the average local field. Okay, phi naught is the magnetic flux, and if lambda is the radius, okay, then phi naught by pi lambda square will be the average magnetic field which is present within the vortex core. And this, you know, is roughly true because here your at a distance outside lambda, the flux is decaying exponentially, is exponentially small, and then it becomes roughly constant. Okay, in this, so it decays exponentially, and then here it is actually varying logarithmically, it is changing very slowly, and then over the vortex core it is constant. Okay, over the vortex core it becomes constant. So you know, the flux change is very weak. Okay, so the flux change is very weak. Okay, over the, so within this region of lambda, okay, within lambda, the average magnetic field is nothing else but the magnetic flux quanta phi naught divided by pi lambda square. And you don't make too much of an error when making this estimation, so, or this approximation. So this is an approximation that we will use to justify certain things that we will in our calculation, certain aspects in our calculation. So the average local field within, the average local magnetic field which is present within this region, the average local magnetic field which is present within lambda is roughly phi naught by 2 pi lambda square. We have the exact expressions, but they are not very different from this value that you will have. Okay, so let us now look at the energy of a vortex line. So the energy of a vortex line will be equal to kinetic energy of the Cooper pairs which are forming the current circulating around the vortex. Kinetic energy of the Cooper pairs forming the current circulating around the vortex. Okay, so around the vortex you have currents which are circulating, and the kinetic energy of those Cooper pairs, so you know that around this vortex you have currents which are circulating. So the kinetic energy of the electrons which are the kinetic energy of the particles which are forming this current, that will be contributing to the energy of the vortex, plus the magnetostatic energy due to the magnetic field of the vortex. Okay, so this will be the magnetostatic energy due to the magnetic field around the vortex. Okay, now you will consider that this vortex has a length L. Okay, so first let us calculate the kinetic energy. The kinetic energy of the Cooper pairs circulating around the vortex, which form the current. This is the current. This is equal to integral dq bar half m vs square times ns. This is the density of Cooper pairs, and this is m star is equal to twice of m. And recall that Vs is equal to nothing but J by ns E star, where E star is twice of E. Okay, so therefore if I plug that in there, okay, then this will be nothing else but integral of dq bar, where I integrate over the entire volume of the integration is over the entire volume around the vortex, okay, including the vortex, okay, and this will be half of m star by ns E star square into square of Js, and lambda, which is the penetration depth, is m star by ns E star square into mu naught raised to half. So therefore the kinetic energy will be equal to integral d cube r mu naught into lambda square mu naught by 2 lambda square Js square. Okay, and so this will become equal to half mu naught lambda square integral of Js square d cube r, and you know that Js is equal to 1 by mu naught curl of B. Okay, so this naturally becomes equal to half of lambda square by 2 mu naught. Okay, so let us rewrite this as lambda square by 2 mu naught integral of curl of B the whole square d cube r. This is the kinetic energy contribution. Okay, now if you look at the magnetostatic contribution, the magnetostatic contribution will be magnetostatic contribution to energy will be integral of d cube r B square. Okay, so this is the square of the magnetic field of the vortex. Now we had already approximated that most of the B is from within lambda of the vortex. So within a distance lambda, within a distance lambda of the vortex, within a distance lambda of the vortex. Okay, so what is going to be this contribution? Let us approximate it. So the average magnetostatic energy contribution will be integral d cube r average of the field, okay, where you will look at for r less than greater than xi less than lambda. We will be basically looking at this distance where you are looking at a distance r, which is, so basically you are going to look at this vortex. So you have a vortex which is almost like a line, okay, because this is xi and you are in the extreme type 2 limit. So we are basically working in the extreme type 2 limit, where xi is much less than lambda, okay. So you have your lambda which is present here, okay. This is your distance lambda, and you are going to, now if you want to calculate this quantity which is integrated over this region which is extending over a length L of radius r, okay, so this integral d cube r just represents integration over a cylinder of radius r, okay, integration over a cylinder of radius r and length L, then the amount, and b square is the average magnetic field which is present in this over a distance lambda. B square is the average magnetic field, present over a distance lambda. B, if you recall, which is phi naught by pi lambda square. Then integral of b square d cube r b square, this average would be roughly integral of phi naught by pi lambda square, the average local field, into 2 pi r dr into L, okay. This would be the average local field, and you will do an integration from xi to lambda, okay. And this would be, of course, phi naught square by pi square lambda raised to 4 into, this would be pi r square from xi to lambda into L, okay. This would be the average contribution. So this would be roughly phi naught square by pi lambda raised to 4 into L, of course, is there, which is the length of the vortex, into lambda square minus xi square. And as we are working with lambda extreme type 2 limit, that lambda much greater than xi, so this would nothing else, this would approximately be phi naught square by pi lambda square, okay. This would roughly be the magnetostatic contribution. So the magnetostatic contribution would be d cube r b square would roughly go like this, okay. This would be the form of the magnetostatic contribution. Now the magnetostatic contribution has 1 by 2 mu naught also, so this would basically give rise to this other additional factor. If you take care of the units, then there will be 1 by 2 mu naught. So the net this would be the contribution from the magnetostatic energy. Now let us go back to the kinetic energy contribution, and if you look at the kinetic energy contribution, that is, this is the kinetic energy contribution. So let's write that down. The kinetic energy contribution now would be lambda square by 2 mu naught integral d cube r curl of b the whole square. And if you recall Js, which is curl of B was equal to, we had already shown, phi naught by two pi lambda square mu naught into 1 over r. Okay, it goes as 1 by r. Okay, so and there was a theta cap. So now j square, because we are going to consider the magnitude, we will not consider the vectorial form. So the kinetic energy contribution would basically go as the kinetic energy, because the kinetic energy term contribution would basically go as phi naught square by 4 pi lambda square mu naught. Okay, integral of dr by r, if you are integrating from r, which is going from xi to lambda, and this would basically give you a contribution to the kinetic energy as 4 pi lambda square mu naught log of lambda by xi. And into L, of course, there would be a factor of 2 pi. Integral d cube r, I forgot to mention, would be integral 2 pi r dr into L. Okay, so there would be a factor L which will come here, and this 2 pi will actually take care of these additional terms. Okay, and you would have this factor which will be remaining. Okay, so there would be into a factor L. Okay, so the total energy of a flux line, the total energy of a flux line would be equal to, of length L, a flux line of length L would be phi naught square by 4 pi lambda square mu naught into L log of lambda by xi plus the magnetostatic energy contribution, which is phi naught square by 2 pi lambda square mu naught into L. Okay, this would come from here. Okay, so this would give you this extra contribution which is coming from the magnetostatic term. Okay, now typically, because we are working with the because we work in the extreme type 2 limit, therefore the energy of a vortex line of length L is going to be, because log of lambda by xi will dominate, log of lambda by xi will be greater than 1. Okay, where lambda is much greater than xi, so therefore energy of the flux line will basically go as this first term, and we will neglect the magnetostatic contribution. So phi naught square by 4 pi lambda square mu naught log of lambda by xi into L, or E naught, which is equal to energy E. If E is the total energy of a flux line of length L, the energy of per unit of a vortex per unit length is basically phi naught square by 4 pi lambda square log of lambda by xi. So this is a formula that you will see in many textbooks, which gives you the energy of a flux line per unit length. This is the energy of a flux line per unit length, which is phi naught square by 4 pi lambda square log of lambda by xi. And we are working in the extreme type 2 limit where lambda is much greater than xi. Then we can drop the magnetostatic energy contributions because they are much smaller than this contribution. So this is the energy of a vortex line per unit length. It comes about essentially because of the currents, which are strong currents which are circulating around the vortex. This term is basically current contribution. This is the current contribution to kinetic energy, and which dominates over the magnetostatic contribution. Because of the extreme type 2 case, it dominates over the magnetostatic contribution, and the current contribution is a very strong contribution because it has a 1 by r dependence. Okay, as you go towards the vortex core, the current density becomes very large. If you look at here, the current density has the shielding current density has a 1 by r dependence. Okay, so as you are going towards the vortex core, this current density is going to become very strong, and that is why the kinetic energy contribution becomes a very dominant contribution when you are looking at these vortex energy, the energy of a vortex line. So in the next lecture, we will use this to actually calculate the lower critical field of a superconductor. Now, before we end, one would like to say that whereas the above relation of the energy per unit length of the vortex line, namely epsilon naught, has been obtained for kappa, which is lambda by xi much greater than 1, or lambda much greater than xi, if kappa, namely this is the extreme type 2 limit, extreme type 2 limit. However, if kappa is not that large, then the epsilon naught is going to be the energy per unit length of a vortex line is 4 pi lambda square ln lambda by xi plus phi naught by 2 pi lambda square. Okay, this was the magnetic energy density, phi naught, forget. This was the energy density, the magnetostatic energy density, which we had already considered. This is a term from the magnetostatic energy density, which we had neglected. However, if you don't have kappa that large, then that term comes back into the picture, and this is something that you have seen earlier. Phi naught square by 2 pi lambda square, which is the magnetostatic energy density, and you can actually rewrite this as phi naught square by 4 pi lambda square log of lambda by xi plus an additional term 2. Okay, so this is of course also an approximation. We have not done a direct integration, but then it will be, even if you did a direct integration of the magnetic fields without using the average field distribution that we have considered, you would get an expression which is very similar to this, with a few higher order corrections which actually vanish out. But this is going to be to leading order. So if you are extreme type 2, in the extreme type 2 limit, you will essentially consider the first term. Okay, but if kappa is not so large, then it is essentially phi naught by 4 pi lambda square plus an additional factor, which will come into the picture when you consider the contribution to the energy per unit length of a vortex line. Okay,